calculator? I got calculators. I will just have these, so just get them back to the end of class each time. We're to the point. It's way too much math to be trying to use a phone or whatever. Harder. Absolutely. Let's pray and we'll get started. Father, help us as we study and learn these things. Help us, our minds, to grasp them. Help us to be diligent in our studies and the things that we've studied bring to our remembrance. And, help me to teach clearly so that these things are intelligible. And Lord, help us all to care more about things that are of true importance. Moles and grams and all this only goes so far in life, and they will all pass away. I pray this in Jesus' name. All right. Well, where did we leave off? Because my video cut off last time. Normally I go back and check the video. I'm like, okay, we were on this problem, but I couldn't do that last time.
The last column I have written down is 1.50 G or grams of N2, and you're trying to send that in, or I don't know.
Did we do CCl4 plus CF? No, we didn't. That's yields. Let me see somebody's problem. You have it. You were taking a test. You don't have it. What do you
I
have?
think the last one was the base solid one. This one.
Grams
Or-
of SI. Did I make this one up or was it out of the book? Oh, I think I know this one. Okay. I gotta find it. Do you have C3H8 plus 5O2?
Yes.
Okay, and then do you have NH4 2SO4 plus CaOH2?
Yes.
Okay, good. And then do you have C8H18 plus 5O2?
Yes.
Skip. Okay, we did that one. Okay, good. Fe2O3 plus 3CO?
No.
Okay. Okay. Well, let's do that one. Must be where we're at. All right. It says, what mass of carbon monoxide, CO, is required to react with 25.13 grams of iron oxide according to the equation? And here's the equation. It is Fe2O3 plus 3CO yields Fe plus 3CO2. Let's go back to our question. What mass of carbon monoxide, so it wants this in grams, right, is required to react with 25.13 grams of this? Okay. Where would I begin?
25.
Got to start with what I have. I'm going to just say this from looking at the test, and I understand why now more. Your math on many was broken up. That was not helpful. You really want to end up with a long linear equation where you can see everything so that it doesn't get messed up. So we're going to put 25.13 grams, and and we're going to label this. 25, that was another thing I saw, was labels were not there. 25.13 grams of FeO3, Fe2O3. I can't stress enough the labels, okay? I was doing my own, just getting ready for today, and I had some where I was just trying to go fast because I was running out of time, and so I skipped labeling. And all of a sudden I'm doubting everything I'm doing because I'm like, wait, what moles are those? What grams are those? And so I had to go back, scratch it out, slow down, redo it. It's just, this is the process. And I was a kid, I hated it in math when they were like, oh, show all your work. That drove me nuts. I'm like, this is too stupid easy. Why would I do this? But then, you know, here it is. So, all right, I got this. I'm looking for this. How do I begin to get from some measure of this to some measure of that?
Moles.
Yeah, I want to get to moles, right? So I can take this and I can multiply it by my formula mass, my molar mass, right? So I got moles on top here, or I got grams on top here, so I need them on bottom here, right? So grams of Fe2O3, and of course up here I'm going to have for 1 mole of Fe2O3. So find me a formula mass for this, or a molar mass for this, Fe2O3. Periodic tables and calculators, let's do it. How do you know what? So get a calculator now.
I got 89.993.
So what'd you get?
I got 159.687.
Okay. What's the molecular mass of iron?
Not the wrong one.
Okay.
Alright, it's 55.845.
55.845.
Yeah.
Okay, so let me do that. 2 times 55.845 equals plus 3 times 15.99. That ought to give me 159.66. Okay. All right, so that, when I look at this, I've got grams of iron oxide canceling. I'm now down to moles, right? So now this is where the stoichiometry comes in. I do a mole-mole ratio. And so I need my moles of Fe2O3 on the bottom. And I need moles of carbon monoxide on the top, right? How many moles of carbon monoxide in this ratio? 3. How many moles of this? 1. So that'll land me in moles of carbon monoxide, but my question is, how many grams of carbon monoxide? So now I just need to multiply this times moles per gram, right? So moles of CO on bottom, grams of CO on top. Mole of carbon monoxide is going to be what, like 13.01 grams? Okay, so run that math. What'd y'all get?
I got the 1 mole of CO is 28.001.
Grams?
Yeah. There.
I did CH. Wow. Okay, that'll change everything, won't it? Read me that number again.
28.001.
28.001. Thank you, sir. Yeah, that's a good reason not to trust me. All right. So let's do it again. 25.13 times Okay. It's going to be grams of CO, carbon monoxide. Okay. So let's turn the page here. Make sure that we got the right answer. 13. Yeah, they like that. Okay, good. All right, we're now going to do reaction yields. All right. We talked about limiting reactants last time?
Yeah.
Thought we did. Thought we did this. Didn't we do this? Identify the limiting reactant.
We did.
3 Si solid plus 2 N2 yields Si 3 N4. Was that the last one that you were telling me about, Ingrid?
Sorry?
Is that the one you were telling me about, the 3 Si solid plus 2 N2 growth? Okay. We did that. All right. Well, did we calculate percent yield? Did we do copper sulfate plus zinc? Okay, well that's where we're at then. Let's do it. Upon reaction of 1.274 grams of copper sulfate, CuSO4, with excess zinc metal, you get 0.392 grams of copper metal. Okay, so we'll write out the formula here. It's CuSO4 aqueous plus zinc solid yields ZnSO4 aqueous plus Cu solid. Okay? So now what we're looking for here is what's called a percent yield. Okay? We reacted this much. We yielded this much in reality. That's not, but there's a hypothetical. Everything we've been doing so far has been hypothetical yields. In a perfect world, if every single atom reacted the way it was supposed to, and I didn't drop any, and I measured everything perfectly, this is what I ought to get. But then you go into the lab and you do stuff and you're off by quite a bit. And that's pretty normal. So that's what we're doing here. We're going, hey, this is what we should have had, this is what we get, what we did get. What's our percent yield, okay? So first thing we want to do is figure out how we should get. What's our hypothetical yield, okay? So I'll begin here with this. 1.274 grams of CuSO4 times, and I need to multiply it by its formula mass, right? So I need mass on top here, I need it on the bottom. I need the formula mass for copper sulfate. If you guys could do that for me. 1 mole of copper sulfate. I'll be real honest with you, when I'm sitting here doing my computer, I just type in molar mass of CuSO4 and it, does it for me really fast. Might be the way to go for us right now. Molar mass of CuSO4. See what we get. It's 159.609 grams per mole. Okay? So that's going to get me moles of copper sulfate. I ultimately need to get over here to mass of solid copper. So I'm going to do a mole-mole ratio, right? That's my stoichiometry. I've got 1 mole of CuSO4. It's going to yield 1 mole of copper solid. Now all I need to do is convert to grams and I'll know how much I have, right? So I do 1 mole of copper, solid, and I just need to know what's the formula mass for copper, for solid copper, what's the molecular weight?
63.546.
63.546. So what am I going to get when I run this math? What number is this going to be?
It was 100%.
This is a 100% yield, a hypothetical yield, right? So go ahead and run your math and tell me what that number looks like. Point 507?
Yeah.
Okay. So now to get my percent yield, right, I take what I actually got, I divide it by my hypothetical, multiply it by 100, so I get 0.392 grams over 0.507 grams. I multiply that times 100, and I get 77.32.
Yeah.
77.32%. The book says it's right. Let's do another problem. Sorry, I'll give you a second to catch up. Do you need a minute here, Ingrid?
No, I'm just writing extra notes. You're good.
Okay. All right. All right. So our next question is this. What is the percent yield of a reaction that produces 12.5 grams of the gas freon from 32.9 grams of carbon tetrachloride and excess hydrofluoric acid? So here's what this looks like. I have CL4 plus 2 hydrofluoric acid yields freon CF2Cl2 plus hydrochloric acid. This is what is the percent yield of a reaction that produces 12.5 grams of this gas. This is our actual yield, right? And we began with 32.9 grams of this. So by now we should be pretty familiar that we're going to go from this, use our formula weight to convert to moles. I'll do my mole-mole ratio to figure out how many moles I have. I'll use the formula mass of this to get to a hypothetical yield. Then I'll divide my actual by my hypothetical, multiply by 100, and I'll get my actual, right? So without even putting in numbers, I'll just say this. I've got my grams of CCl4 times my moles, my formula mass, 1 mole and whatever it is of grams of CCl4. Then I'll multiply that by my mole-mole ratio, which in this case is just 1. That's nice. 1 mole of CF. You can do better than that. CF2Cl2 over 1 mole of CCl4. I multiply it by my formula mass, right? So that's going to be grams of CF2Cl2 over the 1 mole of it. Right? And that's going to give me my hypothetical yield. My theoretical yield. And then all I have to do is take my actual yield, 12.5 grams, divided by my hypothetical, multiply by 100. That's going to give me my percent. Y'all run those numbers real quick. one did not merely Google formula masses the last time I had a chemistry class. I would sure take advantage of it if I were you. What's the formula mass of carbon tetrachloride? 153.823.
Yeah.
Okay, and what's the formula mass of Freon? Still working on that one, okay. You doing it by hand?
Yeah.
Oh my goodness. I can't. Now that I've seen the light. Of course, you know, I'd probably mess up on a test or something where I couldn't Google. You get it right. But I'll beat you today. 120.91. Right. We've already know this one is 32.9. That 25.86 grams is your hypothetical yield. So now I just come up here, I write that in, 25.8. I've already done this math, so I can proudly say that the answer is 48.3%. By the way, in a lab, you don't always come in under. Sometimes you get like 120% of what you should have got. Many sources. That's usually a major section on a lab is what are the sources of error here? We do okay on this one? All right. Let's go to the next. All right. Talking about titrations. So I need to talk to you about titrations. Titration is a procedure where you'll have a certain known quantity of a substance here. I'll know, at the very least, I'll know what volume or what mass I have in the solution, okay? But I'll ultimately probably be trying to determine its molarity, okay? And so your book talks about this. You may have vinegar in here, acetic acid. So you have milliliters of acetic acid. Well, and I want to know the molarity of this. How many moles in this given amount? And so what we'll do is we'll react it until it won't react anymore. That is the goal, okay? And so I might take. This is usually set up with what's called this is a titration. You set it with what's called a biuret. Looks kind of like this. It's got like a stopcock thing on it. You turn this. If I turn it wide open, the liquid just shoots out. You would never want to do that. You want it so it just drips. In the beginning, you want it dripping quite a bit because it's all going to react. But as the reaction slows, you want to turn that thing off and then just drip a drop. And then just drip a drop until it won't react anymore. And so this will have some, basically like a test solution in it, okay? And this will have a known molarity. And I will figure out the volume, okay? If this thing has, I know what volume I started with. I'll get an end reading when the reaction completes. I'll subtract. I'll know how many. I'll experimentally determine the mass or the volume of a known molarity for a reactant. Well, if I know the volume and I know the molarity of one of the reactants, and I know the volume of the second reactant, I can calculate the molarity of the second reactant very easily. Okay? They, in your book, describe this being done with acetic acid and I wasn't familiar with this reaction so much. With acetic acid and potassium carbonate is the one they're using. And so it fizzes. It's much like the baking soda and vinegar reaction. I am much more familiar with these where you get, so I got a clear liquid, but when I drop this, it might turn purple or it might turn yellow. Now, as it sits, it dissolves. But once this is completely reacted and there's no more reactant and all that I'm left with is product, then this will maintain its color, and now I know that my reaction is ended. But the main part here is this. I will experimentally determine the volume of a known reactant of a given molarity to react with a known volume of another reactant where I'm trying to find the molarity, right? Then I'll do my normal stuff to figure it out. So let's put those principles to work for us in this problem. This is a 20 milliliter sample of aqueous oxalic acid. Oxalic acid looks like this. It's H2C2O4. Was titrated with a 0.09115 molar solution of potassium permanganate. That's KMnO4. Gives us the net ionic equation down below. It says, let me put this part. It says we have 20 milliliters of this. And the molarity is 0.09113 molar. Okay? Here we go. And the volume of this is 23.24 milliliters. So we put this into our equations here. This would be my unknown molarity. I've got a volume, in this case, of 20 milliliters, okay? I'm titrating it with something in here. I know my molarity. My molarity is 0.09113 molar. Experimentally, I determined the volume required for this is 23.24 milliliters. I have everything I need now to solve for the molarity of this using stoichiometry, right? My formula, or my net ionic equation on this thing is this. It's 2 MnO4 plus 5H2C2O4 plus 6 H plus yields 10 carbon dioxide, 2 plus 2 manganese ions plus 8 waters. Okay. Let's go back. Let's think about this. I know this. I know that I have 23.24 milliliters of 0.09113 molar. Should be a K there. Potassium permanganate. I know that I begin with 20 milliliters of this. What I don't know is what is my molarity. Okay, so I'm solving for molarity here, right? So let's begin with this. Right. How do I get started?
We use the molarity formula to find the grid.
Say it one more time.
Use the molarity formula to find the grid.
Okay. That's definitely going to be one of my steps, right? Let's, why don't we start with our volume. So I've got 23.24 milliliters. Okay. I need to go from milliliters to liters because I want to deal with molarity, and that's moles per liter. Right, so 1,000 milliliters over 1 liter. This is where I made a mistake already. We want to label what everything is, right? So this is going to be KMnO4. All this is going to be KMnO4. So at this point, I am to liters of potassium permanganate, right? Now, when I multiply that times my moles per liter, which is my molarity, right? So I'll go 0.09113 moles over 1 liter. Then my liters will cancel out. I'll be left with moles of potassium permanganate. Right. Okay. Now I can do my mole-mole ratio. I can get from moles of potassium permanganate to moles of the oxalic acid. How many moles of potassium permanganate do I need? It's going to be here, actually. I need 2 moles of potassium permanganate. That's going to go on the bottom. That's going to react with 5 moles of oxalic acid. Which is H2C2O4, right? Okay. So that puts me into moles of oxalic acid. I have 20 milliliters, right? So if I put mole, I need to get to moles per liter. I've got moles per milliliter. So I need to go over 1 over 20 mLs, right? And then of course I can put that to 1,000 mLs over 1 liter. And that should give me what I need there. That'll leave me in moles per liter, which is my molarity, which is what I want. Right? All right, I'm looking at a bunch of eyes that are looking at me like they're dead or tired or lost or something.
Yeah, completely lost them.
Completely lost? Okay. Let's go back to the bigger picture. I know, for one of these, I know my molarity, and I know my volume. For the other one, I know my volume. I just have to get to molarity. Okay. So I start with, over here, I started with my volume,
Yeah.
and I multiplied my volume, and I converted it to liters. Okay?
Yeah.
I guess I could have just written 0.02324, and that probably would have been easier, but skipping the step can be confusing. So that gives me liters. Now I've got my molarity. That's moles per liter. So when I multiply molarity times liters, that just leaves me with moles,
Yeah.
which is what I want. That's what I got here.
Okay.
This is moles of this. I need to get to moles of this. So I multiply my moles of this times my mole-mole ratio, which is 5 to 2. That's where these numbers come from. For every 2 of these, I react with 5 of these. So my potassium permanganate is on top here, so I'm going to put it down here. 2 moles of potassium permanganate reacts with 5 moles of oxalic acid. Okay? So that gives me moles of oxalic acid. I need to get to moles per liter because I'm looking for molarity. I don't have liters yet. I have 2 X's for some reason. But if I multiply moles times milliliters, I'm getting close. I just need to convert from milliliters to liters, and I'll end up in moles per liter of oxalic acid.
So you're ending with liters or milliliters?
Let's check it.
You're ending with molarity.
So I've got milliliters here, right? I'm just gonna erase that. Okay, it's easier than ruining my markers. I've got milliliters here, right? I got milliliters here, right? Okay, so now I'm down to liters. My liters, my liters. Now I've got moles, and I got moles. Now I got moles of oxalic acid. Ooh. That does not have anywhere to cancel, right? H2, what was it?
C2O4.
C2, H2C2O4. So I've got moles of oxalic acid. That does not cancel with anything. What I have initially is moles per milliliter, which is not useful to me. But because I convert my milliliters to liters here, what I ultimately get is moles of oxalic acid, H2C2O4 over liters of oxalic acid. Well, moles per liter is molarity, so this is oxalic acid. It's a bunch of steps. And if I did not have it written out linearly, I would have died. I would never have made it. So this is just one of those things you gotta, here's what I'd like us to do. Let's do this, let's tackle this whole problem from scratch. This time I want you guys doing it with me, okay? We've seen it a couple times now. Let's tackle this whole problem from scratch. It'll feel new. Anyways, because they've been confusing. Here's my net ionic equation. I've got 2 MnO4 plus 5 H2C2O4 yield plus 6 hydronium ions yields 10 CO2 plus 2 manganese ions plus 8 waters. Okay? And I was told that for this I have 23.24 milliliters of a 0.09113 molar solution. And that is reacting with an unknown molarity of 20 milliliters of this. I'm solving for this right here, right? So I can begin with my volume, 23, well actually I'll begin with my molarity. did it before.
So you start with the volume. You started with the volume before.
Okay, well, let's do that. I reckon it'll come out the same either way. 23.24 milliliters times 1/1000 milliliters, right? And of course, I do want to mark what this is, KMnO4, 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 markers, fine, can't throw. All right, so now I'm, at this point, I've gotten to liters of KMnO4, which is good. If I multiply liters times molarity, that will give me moles. So that's where this other comes in. So I go 0.09113 moles over 1 liter, and again this is KMnO4, KMnO4.
Where's the K coming from?
Potassium permanganate.
Oh, okay.
Oh, it is not. It is not potassium permanganate. It's just permanganate. Bless my heart. I am so used to dealing with potassium permanganate, which is really fun stuff. It's bright purple and you can light it on fire and it does tricks. It's blue, purple flames. It's totally cool. Anyway, so used to that, I never actually don't think dealt with permanganate. All right. So here we go. Back to this. We've got moles of permanganate at this stage, right? And I want to get to ultimately to moles of this. So now I'll do a mole-mole ratio. I'm going to do 5 moles of oxalic acid, H2C2O4, over 2 moles of permanganate, MnO4. That gives me my moles of oxalic acid. Right, but I'm looking for moles per liter because I want molarity. Well, it gives me some milliliters. I could just as easily write 0.02 liters. That's actually what I would do. But I'm just, for the sake of it, I'm going to put it the way it is here. 20 mLs of H2C2O4. I'm going to convert that to 1,000 milliliters per liter. H2C2O4, H2C2O4. When everything's canceled out, I get moles per liter of oxalic acid, and when you run this math, you should get 0.2648 molar, or 0.2648 moles per liter. We do hydrochloric acid with sodium hydroxide.
I didn't got that.
Huh?
I didn't got that.
You didn't get it.
423.57.
Well, that ain't right. What'd you get?
Work it out.
Okay, well, let's try this. We'll do our math again.
What did you get the first one?
I got 423.57.
That's 264. We're doing something wrong, hold on.
Try it,
I probably want to try it, bro. I know I'm not gonna get 0.6, but you can try it.
I got the right answer.
I probably did something wrong.
Right. This is why you run it a bunch of times.
Yeah, I'll try again.
I did get this number, this answer. And it's the one I got before, and it's the one that's in the book. How did that go so fast? I just got in here. Got it?
Yeah, I got that.
Andrew, go. Did we do, did I skip one? Did we do hydrochloric acid with the sodium hydroxide? We probably did. I skipped straight to the harder problem, sorry. We probably should have done the easier problem first. No wonder you guys are sitting there like, just moving on. I already did this. All right, let's do the easy problem now. Hopefully it's easy. Hopefully we don't still find this one to be hard. Okay,
I got it on board.
you got it now, good. So this is
Probably did something wrong.
HCl plus sodium hydroxide produces table salts and water. Okay? And 50 milliliter sample of hydrochloric acid. Okay? And it was reached by doing 35.23 of a 0.250 molar solution of sodium hydroxide. And of course, what I want to find out here is my molarity, right? How many moles per liter were in that? So my setup is going to be very similar. Right? I've got, oh, this is mLs, right? So I can go 35.23 milliliters of NaOH. And I'm going to multiply that by my molarity, and then my liters will cancel. I've got 0.250 moles per 1 liter. Oh, I skipped a step, didn't I? You need me to convert this to liters. So we'll go 1 liter over 1,000 milliliters. Now I can come in with my moles per liter, so 0.250 moles over 1 liter of NaOH. So just to recap, I began with milliliters of sodium hydroxide. I multiplied it by a conversion factor to get to liters of sodium hydroxide. I multiplied that by the molarity of sodium hydroxide to get to moles of sodium hydroxide. Now I use my mole-mole ratio, which is conveniently 1 to 1, so that's easy. So I'm going to have 1 mole of hydrochloric acid over 1 mole of sodium hydroxide. That puts me into moles of hydrochloric acid. I need to get to moles per liter for this, so now I just multiply by 1 over 50 mLs of HCl.
See the ratio where it's 1 to 1, how do you know which one's on top and which one's on bottom?
Oh, because I manipulate them however I need to. Since I have I have moles here of sodium hydroxide and I need them to cancel, then I put it down here.
Okay. Yeah, I'm with you.
It's a good question, very good question. So now I have 50 milliliters of hydrochloric acid. I need to get that into liters. So I do 1,000 milliliters over 1 liter. Of course, this is still HCl. And when I run that out, and the math's going to be a lot easier on this one, but the formula is still the same.
Just like 1 liter.
No, well, it's just saying this, whatever moles this is, it's in this much liquid.
No, like the one on top of the 50.
Right here, right? Yeah, it's just a placeholder.
Okay.
That's all it is. It's unitless. It's a good question. Good.
.1761.
Good. That's how you do these. All right. The next one I want you looking at is called gravimetric analysis. So that's where we're going to have a precipitate. We're going to do a reaction. It's going to get a precipitate. That's where a solid comes out of it, and we'll put it through filter paper. You'll weigh your filter paper in advance to know what that is. You'll run the solution through a funnel, get everything out. You'll put it in a drying setup. You'll take its final mass. You'll subtract the initial mass of the filter paper, and you'll know the mass of your product. Great. Now, let's do something with that. And this is where not having a lab setup hurts, because normally we would actually do this, and you would know what I was talking about. But at least you're getting 100% on your labs. Kill them that part. It is a great help. Okay. It says a 0.455 gram solid mixture containing magnesium sulfate, that's Epsom salts, like you'd soak in, is dissolved in water and treated with an excess of barium nitrate, resulting in the precipitation of 0.6168 grams of barium sulfate. So here's what it looks like. I've got MgSO4 plus BaNO3 2 yields BaSO4 plus MgNO3 2. Okay. So it said 0.550 gram solid mixture containing magnesium sulfate. So that's this. So now I've got 0.4550 grams. You can read my chicken scratch. It's 0.4550 grams. All right. It is dissolved in water and treated with an excess of barium nitrate, resulting in the precipitation of barium sulfate, and it yields 0.6168 grams. What concentration of magnesium sulfate is in, what's the percent mass of the mixture? Okay. All right. So here's how we walk through this one. I'll begin with my grams here, okay? So I've got 0.455 grams of magnesium sulfate, MgSO4. All right, I'll multiply that by my formula mass, so 1 mole of MgSO4. And the mass of 1 mole of MgSO4 is 120.366 grams. Okay. Then I do a mole-mole ratio. I've got 1 mole of this, 1 mole of that, so that cancels out very nicely. I still want to put it though, so I see my steps, how I convert it from one to the other. Ben, I'm going to pick on you. Which one goes on bottom?
MgSO4.
That's right. It's going to be 1 mole of barium sulfate. So now I'm into moles of barium sulfate, and I want to multiply that by the formula mass of barium sulfate. So that's 233.38 grams of BaSO4 per 1 mole of BaSO4. At this point, I am to my mass of barium sulfate, which is good. Now, this will give me a theoretical yield. Okay. So run these numbers. What do you get? Should be 0.882.
Yeah.
Okay. So what it's asking me here is what is the mass percent of BaSO2 in the mixture? So to do that, this is what I actually got, right? So I need to go 0.6168 grams of BaSO4. Multiply this by 100. And I will get 69.92. So it's saying mass, this is not the same as percent yield, though it probably looks similar. It's saying mass percent. So I'm not going to go into all that right now. I'm just confused. We're going to leave it where it lies. How much time do I have? Let's take on one more problem. Hopefully we get finished. Last problem for today says, what is the percent of chloride ion in a sample if well, let me just write this up. So our formula is Ag plus aqueous plus Cl negative aqueous yields silver chloride, AgCl solid. Okay. What percent of the chloride ion is the percent of chloride ion in a sample if 1.1324 grams of the sample produces 1.0881 grams of AgCl when treated with excess silver. So we have all of this we can handle. This is in excess. This we don't know, right? But we do know that we're starting with 1.324 grams, okay? All right. So what we can do is begin with, well, what should we yield, right? So if I've got 1.324 grams of Cl, right, I multiply that by my moles, my formula mass, right? And so I'll get grams of Cl over 1 mole of Cl. Then I can do my mole-mole ratio, which is going to be 1:1. 1 mole of silver chloride over 1 mole of just chloride ions. Right? Then I can multiply that by my formula mass. That will give me a mass of AgCl, right? I can also work this in reverse, by the way. Let's pick up here next time. I have not worked through this problem yet. I'll work through this problem. We'll pick up here next time. We'll finish this unit and we'll kind of start the next one. Okay? All right. Y'all have a good day.
My statement left me everything about you.
No, that's yours. I'm not going to be back next year.
Oh, okay.
I'm taking the church. It's a little further away, so I won't be able to be here. So, like, there's no chance of me giving the same tests or anything that kind of stuff.
Okay.